Question 21. A student investigates how a spring stretches. She measures the original length of the spring, adds a 2.0 Newton weight, then measures the extended length of the spring. Look at the data. Okay, I will. 21A part 1. Calculate the spring constant for the spring. Use the equation force, spring constant, extension. Let's use the physics algorithm once again. Force is something we've got up from this table, 2.0 newtons. Spring constant, let's call that K. Oh yeah, they're trying to calculate it, so that's our unknown. And extension equals that one there, 4.0 centimeters. Just to make things abundantly clear, what they're going on here is original length. We've got our, let's call it as a spring. It looks a bit like this. Our original length is 3 centimeters. Our new length is 7. This is roughly to scale, kind of to scale. There we go. So we get an extra 4 centimeters there, 7 centimeters in total. So that's what's going on there. Our extension is the difference between the stretched length and the original length. Now, the spring constants are usually newtons per meter, but I've noticed that in our answer we're looking for newtons per centimeter. We've got our extension in centimeters. Our expected unit is newtons per centimeter, and that's handy because it basically means we don't have to convert this to meters and start mucking around with conversions and things. So force equals the spring constant times extension. Let's call that little x there. You can substitute the numbers in and rearrange it, or rearrange it first, then put the numbers in. I like to practice my algebra, so I'll do the rearranging first. X equals force over, just realised I'm not looking for extension, K, spring constant, equals F over X, there we go, equals 2.0 newtons over 4.0 centimetres, so newtons over centimetres. Don't have to convert anything, just double check that. 2 over 4, a half. Nice. Okay, 0.5 newtons per centimetre. Question 21A part 2 suggests 2 ways that the student could improve and develop their method to find the spring constant. Let's have a look at their method. Measures the original length of spring, adds a weight, then measures the extended length of spring. Fine. Okay, now we need to update this method to get a more accurate calculation of spring constant. Quite a few things we could say here. My go-to would be to get more information and then get the spring constant from a graph. So let's do that. Measure extension for more weights. There we go. Get some more weights in there and measure the extension several times. Plot results on graph and extract spring constant. Here we go, that looks pretty good. What else can we do? Another good thing for scientific method is to take repeat readings to identify anomalies and then calculate averages. So let's do that. Take repeat readings and calculate averages and identify anomalies. It's not enough just to take repeat readings and just say that. Why are we doing it? Well, we're getting averages, we're identifying where our results are a little bit awkward, so that's something we need to include there. Other things you might want to include in this is maybe using higher resolution equipment or repeating the experiment with other equipment, seeing if it still works. But I don't really like those methods because they haven't mentioned the specific equipment the students used to make these measurements here. The method is all about how they're using whatever equipment they've got. So I'd stick to these suggestions. So measure more weights using whatever equipment that they've got. So that's basically repeats. Plotting the results on a graph and then getting lots of data to get the answer, and then taking repeat readings to identify anomalies and things like that. I think those are better method changes than simply changing the equipment to better equipment. Question 21B. The spring constant of a different spring is 40 newtons per metre. Okay. Calculate the energy stored in the spring when it's stretched by 0.20 metres. Use an equation from the data sheet to help you. Don't mind if I do, but before I do that, let's find out what we're dealing with. So a spring constant, K for constant, 40 newtons per metre. Calculate the energy stored. That's the thing we're looking for with a spring when it's stretched to 0.20 metres. So when it's stretched by 0.20 metres, that's what that means. That's good. I don't have to calculate extension first. We've got the extension, 0.20 metres. Right, let's get our equation sheet out. Where is it? Thermal energy, no. Ooh, energy transferred in stretching, nice, okay. So, energy transferred in stretching equals 0.5 times spring constant times extension squared. Interesting. 0.5 times spring constant, 40 newtons per meter times extension squared. Extension is already in meters, so I don't have to convert that. Goes hand in hand with our newtons per meter for our spring constant, so things are going to work out quite well. Just got to make sure we square that 0.2. In comes the calculator, why not? 0.5 times 40 times 0.2, and I can square it. That gives me 0.8 joules. Just double check this. Most calculators are very good at just doing exactly what you've told them to, but if I were to break this down into an intermediate step, I'd put 0.5 times 40 times, let's find out 0.2 squared by itself, so 0.2 squared, 1 over 25, whatever that is, 0.04, so that's our 0.2 squared. Let's calculate that just to double check our answer. 0.5 times 40 times 0.04, 0.8 joules again. There we go, nice. Question 21C. The diagram shows an experiment a student set up to study moments. It looks like they've got a meter ruler that's wobbling about a pivot, and they're balancing some weights either side. The student holds the meter ruler so it's horizontal, adds the weights to the meter ruler at different distances and pivots. I'm betting at some point they let it go, but question C, I calculate the moments, so we want the turning forces. We've got an equation here to help us figure out that stuff. Let's do our 3 Newton weight that side and our 2 Newton weight this side. The moment is equal to the force times distance from the pivot for this one. So in this case, force is 3 newtons. Our distance from the pivot 50 centimeters. 50 centimeters is 0.5 meter, but I've just noticed over here it's got Newton centimeters. The standard turning force or moment is Newton meters, but luckily they've allowed us to have it in Newton centimeters, so we don't have to do any conversions. Nice. Moment is equal to 3 times 50. 3 times 50, 150 Newton centimeters. So that was a 3 newtons weight. 3 Newton weight, here we go. 150 Newton centimeters. 2 Newton weight, same idea again. Force equals 2 newtons. Distance equals 40 centimeters. Moment, so the moment is 2 newtons times 40. I'll do that one in my head, take a risk. 80 Newton centimeters, that's our 2 Newton weight. Question 21C part 2. Which way will the meter ruler rotate when it's released by the students? Ah yes, it said up here that they held it horizontal and they put some weights on and they're going to release it. Here they are releasing it. So the greater moment will be the direction in which it twists. So our greater moment is the 151 here. That's this weight here. So our ruler is going to drop down this end and this end will be pulled up. So the best way to describe this would be to describe it in terms of the clock. So it'll be twisting this way. That's against the way a clock normally goes. So anti-clockwise. You could also get away with saying the left-hand side will drop downward, because that's what will happen in our picture. If you're not confident talking about analog clocks.